The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, hi. So, coming toward the end, our goal, and certainly to reach next week, is partial differential equations, Laplace's equation. But additional topics still to see clearly in 1D. So one of those topics, these will both come today. One of those topics is the idea, still in the finite element world, of element matrices. So you remember we saw those, that each bar in the truss could give a piece of A transpose A that could be stamped into the, or assembled, to use the right word. I think assembled is maybe used more than stamped in, but both okay, into K for graphs. An edge in the graph gave us a little 1 minus 1 minus 1 1 matrix that could be stamped in. And now we want to see how does that process work for finite elements, because that's how finite element matrices are really put together out of these element matrices. Okay, so that's step one. That's half today's lecture. Step two, problem two, now coming from the next section, is fourth order equations. Up to now, all our differential equations have been second order. Are there fourth order equations that are important? Yes, there are, for beam bending. So I'll describe that application, which leads to fourth order equations. Do they fit our A transpose CA framework? You bet. You know they will. So each additional application in the framework kind of gets us comfortable, familiar with that framework, what it can do, the A transpose CA. So let me start with element matrices. I'll get the homework, those numbers will get posted on the website later today. I just thought I'd put them down, and I have to figure out what would be a suitable MATLAB question. So my idea for this homework, as it really was for the last homework, was that you get not a large number of ordinary questions, paper and pencil questions, and one MATLAB question. And when I wrote MATLAB last, people interpreted that as last MATLAB. But those words are not commutative, right? So I just meant you, and it didn't really matter. It was a dumb thing to say. I meant you to put the MATLAB question at the end after the regular questions. Sorry. So that MATLAB is due. Maybe a bunch of those turned in on Monday, didn't include the MATLAB, no penalty, but can you, so I'm talking now about the MATLAB for the trusses. Can you, how many have still got a MATLAB for the truss still to turn in? A number. Oh, not too many. Okay. Anyway, just when you can, in my envelope is good. Okay, so it'll be a similar thing for this week, and then, and because it's short, I said, okay, let's get that cleaned up by Monday, and then we're ready for vector calculus, partial differential equations, two and three dimensions, the next big step. But if I want to illustrate element matrices, the best place I could do it would be to go back to our piecewise linear elements in 1D and see how an element now is just one of those little intervals, little pieces of the whole structure. If it's a bar or whatever it is, I've cut it into pieces. Here's one piece. Here's another piece. With finite differences, if I gave you unequally spaced meshes, if my little h is different from my big H, we'd have to think again. I mean, there would be some 3-point instead of -1, 2, -1 for the second difference, you know, it would be a little lopsided, of course, when the mesh is unequal. We would have to think that through for finite differences. For finite elements, the system thinks for us. So I just want to show how that happens. So I'll take this. What's the element matrix for our standard equation for that element? Okay, and then it would fit into the big matrix K. I'm going to come up with a matrix K that I could do in any other way, but this is the way it's really done. So I look in that interval. I'm focusing on that interval. So here I've drawn the basis functions, but now I'm not going to operate so much with basis functions. Let me just think about that interval again. That's the same interval. So those were the basis functions that went up to height 1. One started at height 1 and went down. One started at height 0 and went up. But it's their combination, of course. Let me number this node number 0 and this node number 1, just so we have some height u0 here. So it's really, this is coming from u0 times that hat, and some other height u1 here, which is coming from u1 times that hat. But inside this interval, my u in this interval is u0 times that first hat function, the phi0, the coming down hat, plus u1 times the phi1 function, the going up hat. It's a linear function, so it's going to be there. That's my graph of, oh no, yes, this is u of x. U of x. Okay. Right? I'm focusing inside one element, one interval. I've numbered them 0 to 1, but of course that distance is h. Okay. So there's my function, right? Everybody agrees that this combination, it starts out right, it ends up right at height 1, at height u1, and it's linear, so that's got to be right. So really, what's the contribution from that element? I look at the quantity that I have to, and I'm always taking the phi functions to equal the v functions. So I can write this as c of x du dx squared dx. That's the over the whole thing, over the whole interval would be the u transpose k u. This, everybody remembers that the k part, of course, comes from the left side of the problem. It comes from integrations, and this du is now a combination of all with weights u0, u1, u2, u3. If I plug in for capital U and do all the integrals, I'll see what k is. Now, what's the point? The point is, when I did those integrals, the question is, how am I going to do the integrals? Do I do them the way I did before? Was I watched what phi0, one phi times another phi, and I integrated. That was successful. But the new way is integrate it an interval at a time. Do the integrals. So now so this would be k global. Now I'm going to go just from 0 to h. If I go from just 0 to h, that's going to give me the k element piece, the little piece that comes from this little interval. And on that little interval, this is my formula for u. I'm just hoping you sort of see this as a reasonable idea, and then when we do the integral, you'll see it clicks. Okay, how does it click now? So what's my plan? My plan is, here's my function, there's its picture. I'm just going to plug it into here. Oh, it's going to be simple, isn't it? What's the slope of that function on that, in that element, on that interval? What's du dx? So I'm just doing, instead of doing every full integral for each separate phi, I'm doing every element integral for both phis. That, see, these two phis are both coming in to that element. Okay, so what's du dx? Oh, I mean, this is, I didn't realize how neat this was going to be. So what's du dx in this element? I'll use a different board here. So it's an integral then from 0 to h of whatever my c of x might be. And I'll make a comment on that. But my focus here is what's du dx? What's the derivative? And then I'm going to square it for this function, for that picture. The slope is obviously u1 minus u0 over h, right? The slope is u1 minus u0 over h. And I'm squaring it dx. Okay. Let me take c of x equal 1, just because to see clearly what's going on. So c of x is just going to be 1. Okay. So I'm claiming that this is my u transpose, my little piece. Why is it only a little piece? Because it only involves 2 of the u's. It's going to be a little 2 by 2 element matrix that comes from this element, and then it's going to be put into the big K, the global K, in its proper place. Okay, well, this is trivial, right? This is a constant, this is a constant. The integral is just h times u1 minus u0 squared over h squared, because that's getting squared. The interval was length h. I think I just have a 1 over h. So this is my u transpose k element u. And now I want to pick out what's that matrix. What's that little 2 by 2 matrix that only touches these 2 u's? What's the matrix? Well, since it only touches these 2 u's, you can tell me. I want a u0, u1. Let me make a little more space. And you can tell me what matrix goes in there. I want this all to match up. u0, u1. And now here's the 2 by 2 element matrix, u0, u1. What's the 2 by 2 matrix that will correctly produce this answer? I'm just shooting for that answer. What do I have here? This is u1 squared minus 2 u0 u1 plus a u0 squared, right? And I have to remember the 1 over h, so it's automatically going to come out right. So there's a 1 over h. Shall I remember that first off? 1 over h is part of my element matrix. And then what are the numbers that go inside that matrix? This is, so we had practice with this. You remember when we talked about positive definite matrices way back in chapter 1? The point was that we could look at eigenvalues or pivots or something, but the core idea was energy. The core idea was that energy, that quadratic, and that's what we're looking at again. That's the energy. That's the energy right there, and this is the energy in the finite element subspace. All I'm saying is, what matrix, what 2 by 2 matrix goes with u1 squared minus 2 u0 u1 plus u0 squared? just tell me what to put in that matrix. What do I put here? 1, right, because it's multiplying u naught, u naught. What do I put there? -1, good, because I have a -2, but I've got, it comes in, -1 comes in twice, and a 1 goes there. So there, with the 1 over h included, is ke, k element for that element, for the big H element. You see, it just, I mean, you'll say big deal because we've seen this thing before. Notice what is nice, that when first of all, notice how nice that is. It's particularly nice, of course, because I took c of x to be 1. Oh, so let me make a comment about, suppose c of x was not 1. What would I do? Suppose c of x, suppose I have some variable stiffness in the material. Suppose the material could be changing width. So its stiffness would change. So in other words, I'd have a variable c of x that I should do the integral. Probably finite element systems aren't set up to actually do the exact integral. What would they do? They would take, for that simple integration, they would probably just take c of x at the midpoint. So there's a numerical integration here in the creation of these element matrices. And numerical integration is just take a suitable combination of the values at a few points. Do you know Simpson's rule? Like Simpson's rule, that's a high level, pretty high level rule. My suggestion there was just a midpoint rule. Just take c of x at the middle of the interval. Then it would factor out. So I should really put a c here. I mean, there should be a C should really be coming in there, and you expected that, right? From the A transpose CA, we always saw a C in the middle. It really should be there. When I took C to be 1, I didn't see it. So what am I doing? I'm approximating C of x by C at halfway. Approximately, I would replace this unpleasant, possibly varying function by c at a point and use that value. Yeah, so numerical integration is one part of the picture that we won't go into all the different rules. There's a rectangle rule, there's a trapezoid rule, very good. There's the Simpson's rule, that's better. As I get higher order elements like those cubic elements I spoke about, the numerical integration has to keep up. If I was integrating cubic stuff, I wouldn't use such a cheap rule. I would go up to Simpson's rule or Gauss's rule or somebody's rule. Anyway, that's the C part. Here's the part that stamps into the matrix. Notice, by the way, when I stamp it in, just like tell me how it's going to look stamped in, and then I've completed it. So here's my big K. Wish I had a little more room for it. Okay, here's my big K. All right, so that interval that I drew there, the H interval, will stamp in here, some 2 by 2, right? Now, where will the similar thing coming from this guy, so maybe it has to be numbered -1, sorry about that. That will have, that's another little interval. I'll do the same thing on that interval. I'll get a little element matrix, 2 by 2 guy for K for that element. And where will it fit in to the big K? Does it fit in up here? Let me just ask you. Does it fit in up there? Yes, no. I'm assembling, stamping in the small 2 by 2s into the full n by n. And just if I draw the picture, you'll see it. So when I do the 2 by 2 for that big H interval, it goes there, let's say. Then I just want to say, where does the 2 by 2 go for the interval to the left? Does it go there? Nope. How does it go? It overlaps, right? It overlaps. Because, why does it overlap? Because the phi naught, this guy, is acting on the right and also acting on the left. The u naught is controlling, is active, is partly controlling the slope this way and also that way. The u naught is in common to the two intervals. Anytime, any unknowns, any mesh points that are in common to two elements, we're going to have an overlap when we assemble. And so it'll just sit right there. And so there is the diagonal guy, and maybe you could tell me what number will go there. What number would actually go there, and then you'll see the whole point of assembly, stamping in. Well, what number goes there from this? 1 times the c over h, correctly. So in here would be the c, can I call it c right? Because it's, or c big H, c on the big H interval, divided by the h, because that 1 we had to get it right. And then what will go in that very same spot, so added in, coming from the small h interval? The same thing, it'll be this 1, like shifted up, right, moved over. So it'll be coming from that 1, so it'll be a c on the little h interval divided by little h. That would be the diagonal entry of k. That's what we would see right there. Over here, should I write a typical row of k? Typical row of k, when I do that, is going to have this c little h over h plus c big H over h. That's like the 2, right? That's like the 2. And what goes here? What will the entry be that sits there and when I assemble? Just this guy, right? Just this guy times that. The entry here will be the minus CH over H. That'll be the entry. This is the diagonal one. This is the one to the right. And what's the one to the left? What's the one here? Well, you know what it is. It's going to come from the minus, and it'll be the minus C little h over little h. Look at that. That just shows you how it works. And again, you can look at that to page 299 to 300 in the book. You see that it's, if the C's are the same, if the H's are the same, then we're looking again at our minus 1, 2, minus 1 times whatever C over H to keep it dimensionally right. Do you see that? It's just simple. Simple idea. The point is that each interval can be done separately. You know, it's a simple idea in 1D. It's a key idea in 2D, where we have triangles, we have tetrahedra, tets. We'll see this in 2 dimensions when we, later in this chapter, when we're doing Laplace's equation. And yeah, it's just fun to see it work. You'll have different triangles, say call them triangles, okay? So that phi, do you want me to look ahead? Just 10 seconds to triangles. So imagine we have triangles here. So we have piecewise, we have little pyramids. Instead of hat functions, they grow to pyramids. So there's a pyramid guy whose height is 1 there and drops to 0 in all these places. And that's our phi. Our trial function, test function, will be a pyramid function then. But I can do integrals that way, or I can take the integral over a typical triangle. So a typical triangle is involved with 3 Now I have three functions in the linear case controlling inside that triangle. So what will be the size of the element matrix? Just can you sort of see how the system is going to work? And then we'll make it work in 2D. If I have every node, every mesh point corresponds, has a pyramid function, has a U that goes with it. Those U's are the unknowns. And how many of those unknowns are operating inside that triangle? 3. So what will be the size of the element matrix, the non-zero part of the element matrix? 3 by 3. What else could it be? So we'll see what it looks like. Then we'll have integrals over triangles. Okay, so that's good. Okay, thanks. Exactly halfway through the hour is exactly that first topic of element matrices. Done. Okay. Let me take 2 deep breaths and move to fourth order equations. Okay. Fourth order equations for the bending of a beam. So I better draw a beam. So a beam is this is a 1D problem still. It's a 1D problem still. To keep it 1D, this had better be a thin beam. So this is a thin beam. And the loads. What's the difference? What's new here? It looks like a bar, pretty much, right? But the difference is the load is acting this way. The load is acting that way on the beam. Maybe 2 loads. Maybe a uniform load. Maybe the weight of the beam. But it's transverse. It's in the perpendicular. It's transverse to the beam. It's this way. Okay. So the beam bends. Let me do a fixed free. So this will be a fixed free beam. Fixed free, the word for fixed free would be cantilever beam. Okay. Okay. So that has what happens if I impose those loads? Well, the beam bends. So the displacement is now downwards. Is now not the direction of the rod. The displacement I'm interested in is perpendicular to the beam, downwards. Okay? So we can start on our framework. So this is displacement, u of x. I'll stay with the same letters. Now, yep, so you know I'm going to have an A. That will take me to, well, whatever this is going to get called. What's the quantity there? It's going to be, let's see, what happens? So this is just geometric now. The stiffness, let me put in easy part, C. That'll be sort of the bending stiffness, right? This will be the bending stiffness because the beam is going to bend. And over here, I'll get a suitable W. What I get here, so when the beam bends, it's curvature. Curvature of the beam is what's produced. It's not stretching of the beam, it's curving of the beam. So this quantity E will be the curvature that comes from the displacement. If I displace these beams, suppose I right, put a node here, it's going to bend that down, the bar will curve. So the curvature E. Now then, the question is, what is this A? What is the curvature? Well, do you remember? You're on the ball if you remember the formula for curvature. It's a horrible formula, actually. But that's only because we're going to make it better. Do you remember the curvature of, it was in calculus. Yes, you all remember this, right? Suppose I have a graph. I know its slope. That's become easy now, right? Calculus. But the curvature of it was, what derivative did it involve? Second derivative. And was it the second derivative exactly? No, unfortunately, there's some term which is horrible. 1 plus the first derivative squared all square root. But, I'm just going to take u double prime. I'm going to take just, so this is an approximation. So that means that what is A now? What's my matrix A that gets me from U, or my operator A that gets me from U to E? What's the E equal AU equation? A is just second derivative. That's something new. A is second derivative. And why do I do that? Because I assume small curvature, small displacements. I assume that u prime is squared is very small compared to 1. So it's just slightly bent. A beam that goes way down here, I'd have to go nonlinear. But if I want to keep things linear, I approximate this will be much smaller than this, so 1 is fine. That term goes. Okay, and now the next step will be easy. What's the bending moment? This will be called the bending moment. And let me use the letter W again. I should really use capital M for bending moment. That will be the stiffness times the curvature. That's the force that, the way the spring had a restoring force by Hooke's law. This is the equivalent of Hooke's law, but this restoring force is not pulling back, it's bending back, it's torquing back. And then, of course, there'll be an equilibrium equation to balance the load. So this load is the f of x. And you know what that'll be, because it'll involve A transpose. And the transpose of that, do you want to just make a guess? What will be, I shouldn't use transpose, of course, but I'll use it again. It'll be the same. It'll be second derivative. There'll be, I mentioned, we had a minus sign with a first derivative, but now we're going to have 2 minus signs, so it's going to come out symmetric, second derivative. And the equation here will be W double prime equal f of x. Our framework is working. We have plus boundary conditions on U. And here we have plus boundary conditions on W. So those parts we have not yet mentioned. And of course, that depends on my picture. While we're at it, why don't we figure out what do you think is the boundary condition here? And how many boundary conditions am I going to look for altogether? 4 altogether, because I have a 4th order equation. There will be 4 arbitrary constants until I plug in boundary conditions. So I'm looking for 4 boundary conditions, 2 at this end, 2 at that end now. And what will be the 2 at the fixed end? At the fixed end, obviously, is built in. This is built in. There's slightly different words sometimes for the beam problem. Here I'll have u equals 0 and u prime equals 0. Those apply with A. Those go with A. So A acts on those are the essential conditions, the Dirichlet conditions, the ones I must impose all the way. And now at this free end, what do you think? Well, that's great. It's W equals 0. and W prime equals 0. It's just beautiful the way it all works. So that would be, that's a completely fixed free. Then why don't I draw in, just while we're talking about boundary conditions, an alternative. So here's my beam. And now I'm not, now you see I'm, and it's under a load, f of x, transverse load. Now that would be different boundary conditions. Anybody know the name of a beam that's set up like that? Simply supported. If these, so you don't need beam theory, and I don't know beam theory to tell the truth, to do these problems. So that's a simply supported beam. And what are the boundary conditions that go with that? Well, this is u equals 0. No displacement. It sits there on that support. And what else is happening at that support? There's no bending moment. Nobody's here, right? So it's W equals 0. And at this end too. Also at this end, U at 1 is sitting there, and W of 1 is 0. Yeah. That would be the boundary conditions, 4 of them, for a fourth order equation that we'll just write down in a minute for simply supported. And we could have a mix. It could be simply supported here, free here, I think, or maybe could it be, or would that be, maybe that's too risky. Would that be a singular case, simply supported? Yeah, what would, See, as always with boundary conditions, some are unstable. Some are not going to determine all 4 constants. Just the way free didn't work, right? Free for a rod didn't determine anything. It left a whole rigid motion. Maybe u equals 0, w equals 0 at one end and free at the other end. Is that, maybe it sounds risky to me, but we can see. Okay, so do you get the general picture of the beam? So what's the equation? What's A transpose CA when I put it all together? I'll use that space to put in A transpose CA, the continuous we're talking here. Right now we've got differential equations. So what's the differential equation, A transpose CA? So it's the second derivative. I'm just going backwards around the framework as always. The second derivative of this, and this is C of x times E of x, and E of x is second derivative of u. Equal f of x. Good. In 10 minutes, we've written down the framework, some possible boundary conditions, and the combined A transpose CA equation. I mean, we're ready to go. We've got the pattern to think about this. So let's see, what should we do first? I would say the first thing to do is let's CB1 and solve some problems. Let's CB1 and consider, so if C is 1, it's a fourth derivative equation. Equal, what should we take, uniform load? Yeah. How does a beam bend? Under its own weight. So it's just, 1 or whatever constant. So it's constant load, it's just its own weight, it's going to sag a little in the middle. What's the solution to that equation? And what shall I take as boundary condition? Let me do the simply supported one. So, because that would be kind of nice. So it's simply supported, it's sagging under its own weight with u of 0 equals 0, u double prime of 0 equals 0, because that's the w, and u of 1 equals 0, u double prime of 1 equals 0. Whatever. I don't know that I'll have the patience to go through and plug in all 4 boundary conditions to determine all 4 constants. Just get me to that point. Get me to a solution u of x, the general solution here that's got 4 constants in it is what? Okay. Okay, think again. What are we looking at? We're looking at a linear differential equation. Linear problem. I'm asking for the general solution to a linear equation. What's the general setup? General setup is particular solution plus null space solution, right? You see an equation like that, you're looking for the general solution, tell me one particular solution, and then tell me all the solutions when it has 0 on the right, and we've got everybody. So that was true for matrices, it was true for AX equal B, it's just as true for differential equations. So what's one particular solution? What's one function whose 4th derivative is 1? Actually, yeah? What am I looking for here? 1/4 of x to the, no, what? 1/24th, is it? 1/24th of x to the 4th? X to the 4th over 24? Because 4 derivatives, so we're thinking we're in the polynomial world here. Just as we were with u double prime, with the bar, it was x squared over 2. The particular solution, now we're up to x 4th over 24. So that's the 4th derivative is 1, good. So I'm seeing a 4th degree bending there. And now what about the null space solutions, the homogeneous solutions? When I this accounts for the 1. Now, what are the possibilities if it was a 0? A, you're going to tell me the whole bunch, right? A plus bx plus cx squared plus dx cubed. Because all of those have 4th derivative equals 0. So that's the general solution. Okay. So that whatever the boundary conditions are, they determine A, B, C, D. Yeah, we're not that far away from Monday's lecture on fitting cubics. Actually, we're really close to it. When we use finite elements, we're going to use exactly those cubics. Yeah, I'll get to that point. Let me just, let me take the other model problem that everybody knows what's coming. What's the other right-hand side that this course lives and dies on? Lives on. Delta function, right? Delta at some point. So that's a point load then. I can make it whatever the boundary conditions are. Those will, whatever the boundary, yeah, right. Yeah, good point. This boring stuff will just repeat, right? That's still the null space solution. But now, what is a particular solution? The particular solution has become interesting. The particular solution here was straightforward, simple. That was good one to do first. What's a particular solution to a point load? So instead of having distributed load here, I'm now I'm putting a heavy weight here at this point A. And its heavy weight is, I'm multiplying the delta function by 1. I could multiply it by some L for load or something, but let's just keep it simple. What's a solution to that? 4th derivative equals delta. So that means I've now got to integrate. One way to get the answer here would be to integrate 4 times, right? If I integrate delta 4 times, then I've got something whose 4th derivative will match delta. So do you remember the integrals of delta? Okay, so I integrate. First integral is step. Second integral is ramp. Third integral is quadratic, right? This was linear, boop, boop, linear pieces. The next integral is going to bring me up to quadratic ramp, or quadratic ramp. And the next fourth one is going to bring me up to cubic ramp. Cubic. So it's going to be cubic ramp is what I get there. So one particular solution would be a function that's 0, and then at the point A, it suddenly goes up cubically. So it's 0 here, and it's x cubed over 6 there. I think if I do integrate 3 times, I'll be up to x cubed over 6. Is that right? Yes, cubic. So that's an interesting function. Of course, these parts will tilt the function, will change it, but so our solution won't look like this, because I've only got one particular function, and I'll need these to satisfy the boundary conditions. So there's one particular solution. The general solution, yeah, good for us to think out the general solution. What does that picture look like when I add in this stuff? Well, okay, very, very important. I'm sorry I don't have more space for this highly important picture. Okay, so here's my point A. Keep your eye on that point A. Okay, so to the left of it, I've got some curve, whatever, the beam. And to the right of it, I've got some other curve, whatever it is, And what's cooking at point A? What's the jump condition at point A? That's the critical question. What changes at point A? You remember, this is the corresponding thing, the analog of our ramp. So what changed for the ramp at point A? What jumped? The slope. Okay, now the question is, what's going to jump here? What jumped there? Here, did the function jump? Certainly not. Did the slope jump? Certainly not. Did the second derivative jump? No. No. The second derivative was 0 and then 0. What jumped? Third derivative. The third derivative is allowed to jump. And of course, a jump in the third derivative produces a delta in the fourth, right? It just works. A jump, so I have here, this is a cubic of some sort coming from that junk. This is a different cubic coming from this sort, from this junk and this. And so it's cubic in each piece. Why is it cubic in each piece? Because what's the equation in the middle of that piece? What's our differential equation if I look here? Here's my equation. What is it in the middle of that piece? U fourth equal 0. The delta function is 0 there. And U fourth is 0 here. So of course, this is a cubic spline. We're meeting that neat word, cubic spline. And those turn out to be very, very handy functions for other things too. So we see them here as the solution to fourth order equations with point loads are cubic splines, because the big key point is that there's a jump here in U triple prime, a third derivative. A jump in the third derivative. That's what we saw here, and we'll see it if we have any cubic meeting any cubic. Let me just say, a jump in the third derivative, your eye probably won't notice it. I mean, it's a discontinuity somehow. We don't have the same polynomial from here to here, but that discontinuity in U triple prime it's pretty darn smooth still. You know, the slope is continuous, so your eye doesn't see a ramp. And even more, the curving is continuous. The curvature is continuous. The W, all the E and W are good. It's just a jump in the third derivative. Okay, so I want to speak about splines and more about this and about finite elements for beam problems on Friday, and then that will take care of 1D and we'll move into 2D. Okay.